Well, after starting today with too much personal information, we're ready to get the lecture started. And today is the 23rd video lecture for this class. And I want to start off today reminding you where we were, and that was we were talking about Cauchy sequences. And what we wanted to do is to come up with a theorem that said in the real number line that being Cauchy and being convergent meant the same thing. And what we had proven is if that you were convergent, then you were Cauchy. But we haven't proven that if you're Cauchy, then you're convergent. So we were working towards that, and we had a preliminary result we were trying to prove. And we were in the midst of that, and the preliminary result was that if you're Cauchy, then you are bounded. And so we need to continue that proof. That's what we'll start off with in terms of content when we get started with that. But before that, I want to ask if anybody has any questions about the material we've been covering. Anybody want to ask anything? Yes, ma'am.
Yeah, when we do the proof for if, sorry,
Nothing to be sorry about.
have a monotone subsequence.
Yes. That every subsequence has a monotone subsequence. That's called a monotone subsequence theorem. We use those in the proof. We use this idea of a peak.
Sorry, no, that's not the, if, we're proving Cauchy sequences, if the sequence is Cauchy, and we come up with an m and an n is bigger than or equal to k, does that also mean that m necessarily has to be bigger than or equal to n? Or it can't be equal to n?
It could be equal to n.
Okay.
They could be the same.
I just wasn't sure.
No, there is no order between the m and n.
Okay.
And I think that was if you were, where we used the theorem that you're talking about, is I think we've proven that if you're convergent, then you were Cauchy.
Cauchy.
That's right. And so there isn't anything about a relationship between m and n. They're just both bigger than k.
Yeah. Okay. Sorry.
Okay, that's all. And they're natural numbers. Is that okay? I said okay.
Well, I guess where I'm getting at is that we're finding that the distance between the two of them becomes smaller and smaller within the bounds of epsilon. And so wouldn't they at some point have to get really close together, or is that, they're spots in the sequence, right?
M and n are spots in the sequences, but the spots in the sequences don't have to be very close.
Okay, all right.
So once you get to that k, where all the terms are close to each other with an epsilon distance, it's all the terms. So you could, let's say k was 100,000. Then it says for Cauchiness, is that everything beyond the 100,000, every position, each term in those positions, their distance from each other is less than the given epsilon. And so that means the 100,000th and first term is distance from the 30 billionth term is still less than epsilon.
Okay. All right. Thank you.
Is that okay what I said? Yes, sir, Corey.
Okay, mine in regards to the theorem from Monday and Wednesday last week, where part 1 implies part 2, part 2 implies part 2.
Yeah,
part
it
3
had to
implies
do
part
with
1.
not being convergent.
Could we also prove going backwards, like part 3 implies part 2 and part 2 implies part 1?
Yes, it can be done, I think. I don't know of direct proofs that do that. I haven't thought about it, Corey. I'm sure that there are ones that can be found, but we have done a cycle, if you will, and that's enough to show that they're equivalent to each other.
Okay.
Yeah, but I'm sure it can be done, but I haven't thought. I was just providing the proof that they are equivalent.
Mm-hmm.
Anybody else with anything? Okay, let's continue then where we left off. And I appreciate very much the questions. So where we were was the following. We said, as a theorem, if x of n is a Cauchy sequence, then x of n is bounded. and we were starting the proof of this, and so we let x of n be a Cauchy sequence. And we want to show that it's bounded. So Chuck, what we did was we considered epsilon equal to 1. And then, Melissa, what we had was using the definition of the Cauchy sequence, we know since x of n is Cauchy, there exists this spot, this k, that's a natural numbers number, such that for all m and n bigger than or equal to k, and here we just have any indices being bigger than or equal to k, they aren't related to each other, m and n. M might be bigger, n might be bigger. Okay. I'm not saying it, they're just both bigger than or equal to k. They both could be k. What we have is x of n minus x of n is less than 1, the epsilon. Okay, that's what we had written. We've gone a little further than that, too. So, namely, or in particular, we have, for all n bigger than or equal to k, that's the value of x of n minus x of k is less than 1. So x of k is a particular term in the sequence. Okay? So I'm fixing the k, if you will. K is a fixed number. And the reason that that stems from what we said earlier is because we had m and n bigger than or equal to k. Well, I'm just letting m be equal to k. That's all I'm doing. Okay. Thus, for all n bigger than or equal to k, Megan, what we have is rewriting this as a statement that doesn't involve absolute values. I'd say minus 1 is less than x of n minus x of k, which is less than 1. And Megan, the proof in terms of a Cauchy sequence being bounded is much like a convergent sequence being bounded. So we're going to work in the same style. I'm going to try to isolate the x of n. I want the absolute value of x of n to be less than some positive number for all terms, for all n. So here, Melissa, to get x of n by itself, I'm going to add x of k to both sides. So. But I'm saying this for all n bigger than or equal to k. Here's what we have. So this was a period here. We have minus 1 plus x of k is less than x of n, which is less than 1 plus x of k. Now, to rewrite this as a statement, Corey, having to do with the absolute value of x of n, I need to have x of n sandwiched between a positive number and its negative over here. The first thing that catches my attention, Audra, is that x of k plus 1 may not even be positive. Because x of k now could be a big negative number. Okay? So, Melissa, what I'll do is I'll say, remember, all the work is for all n greater than or equal to k. What I'll do is replace x of k on the left by something smaller and x of k on the right by something bigger. And so what I'll say is minus 1 minus the absolute value of x of k is less than x sub n, which is less than 1 plus the absolute value of x of k. And there should be a period to do that. So for all n bigger than or equal to k, we have the absolute value of x of n is less than 1 plus the absolute value of x of k. So that is something that bounds the terms, the absolute value of the terms x of n. But not all the x of n's, only the n's that are bigger than or equal to k. So what we're going to do to find an m that's positive, it's going to bound all of the x of n's in the not absolute values, is we'll let t equal to. Remember though, this is a bound for most of the n's, x of n's. It's a bound for all the x of n's where the n's bigger than or equal to k. And so the ones before that are just finite in n. So we let m be equal to, the maximum of the absolute value of x of 1, the absolute value of x of 2, all the way up to the absolute value of x of k minus 1, and then 1 plus the absolute value of x to the k. Then the absolute value of x to the n will be less than or equal to m, and that's true for all n elements of a natural number. And that tells us that x to the n was what kind of sequence? Is, hey, all the terms are less than or equal to m inside absolute value. So those sequence is bounded. And that's what we're trying to prove. Remember, what we're trying to prove is that if it's Cauchy, it's bounded. That's the theorem and it's proof. Does anybody have any questions about that? Well, it turns out that that's the only result that we need that's new to prove that Cauchy and convergence mean the same thing in real life. So let me write up that theorem, and let's prove it. So here's the theorem. Its name is the Cauchy criterion for convergence. And it's pertaining to sequences. It's pertaining to sequences. Here's what it says. It says, a sequence of real numbers converges, and I'm going to put this in parentheses, in the real numbers, if and only if the sequence is Cauchy.
So I'm guessing since you put emphasis on that, then it's not true for complex numbers.
I'm not going to say anything about complex numbers. I'm going to say something about, John, I'm very ashamed. I don't think I can answer your question immediately. I think it's true for complex numbers. I'm going to show you a counterexample where I'm not looking at all of R. So I'm going to prove this statement. Complex numbers.
It's just we require all the
All
real numbers.
Mm-hmm.
And
Yeah, and I think it's true for the complex numbers. My brain isn't working as well, but I'll look it up for next time. That's okay. I'm pretty sure it is. So here, no, it is. So here, as an example to illustrate, before we do prove this, to illustrate what I mean, if you look at the space, you know, we normally look at R. We don't talk about the space. We're talking about real numbers. But if you look at, consider our space to be, let's say 0 to 3. Then 1 sub n, 1 over n I should say, my favorite sequence, is a Cauchy sequence. In 0 to 3, but does not converge. In 0 to 3. And really, it's a technical issue. You know, what did it mean for a sequence to converge? So a sequence X sub n converged if there exists this L in R. NR, that's right. So in a smaller space, so my smaller space is from 0 to 3, not including 0. This sequence, 1 over n will converge if there's some L in 0 to 3, such that for all epsilon greater than 0, there exists this k, such that the absolute value of x of n minus L will be less than epsilon for all n bigger than or equal to k. The problem is that the L that it converges to is 0, but it's not in our space, if you will. And so this is an example of a Cauchy sequence that doesn't converge because of the limitation of the space. But in R, we got 0. Does that make sense? We got them all. And so, anyway. Let us prove the theorem. The theorem is an if and only if statement. And one of the parts we've already done in the directions. And we did that before. So here's the proof. This direction, we have already shown that a convergent sequence is Cauchy. We did that earlier. Audra asked about that in some sense today, I think. That's something we've already proved. The other direction with the if and only if statement is here, we will assume, suppose, x of n is a Cauchy sequence. We must show x of n converges. Well, get it away. You know, most of the time for convergence, we say, okay, we want to show that it converges to x, and we'd say, well, we need, we let epsilon be greater than 0 be given, we need a k. But in this case, we don't have a candidate for what x of n converges to. We have no idea what it converges. We just know it's Cauchy. So we'd like to get a candidate, a number, that it's likely that x of n converges to it. So how are we going to come out with this number? Well, here's the way that we do this. Well, since x of n is Cauchy, what did we just prove about Cauchy sequence?
They're bounded.
They're bounded. And then if we apply the Bolzano-Weierstrass theorem, so x of n is bounded. What do we know about every bounded sequence? That's correct. Switch on. So by the Bolzano-Weierstrass theorem, there exists a convergent subsequence, say x of n sub k, that converges to x. Okay. That x that the subsequence converges to is a good candidate for what x sub n can converge to. And that's what we're going to prove. We will prove x sub n converges to x. After all, if x sub n converges, whatever it converges to, every subsequence of it has to converge to that. So that's why x is a good candidate. Got to prove that. All right, so I've got a candidate. So what we're going to do, we're going to let epsilon be greater than 0 be given. What do we need? We need a k. That's right, k is the element of natural numbers. Such that for all n bigger than or equal to k, x sub n minus x will be less than epsilon. Okay, here's what I'm going to know. Note for all n and k, I've already used k. I'm going to change something. In my subsequence, I used k. And now I'm saying I'm looking for a k. Well, I'm going to change that notation. I want to say I want a j. Okay? Just so that we don't get the k's and j's confused. Well, what I want to say is, note for all n and k that are natural numbers, x sub n minus x, which is what I want to show is small, is the same thing as x sub n minus x sub n sub k plus x sub n sub k minus x. So what am I doing to the quantity, the absolute value of x sub n minus x? What I'm doing is I'm adding any term from the subsequence and subtracting that term as well. Is that okay? So this is a particular term, doesn't matter which one, from the subsequence. It's a number. I'm just subtracting and adding that same number. They're the same. There's x of n minus x for any n k that we have. And I know that I can use, what am I going to use next? What have we been using before?
Triangle.
The triangle inequality. So by the triangle inequality, this is going to be less than or equal to x sub n minus x sub n sub k plus the absolute value of x sub n sub k minus x. Now remember, my whole goal is to show that the absolute value of x sub n minus x is less than epsilon. And I know that the absolute value of x sub n minus x is less than these two guys added together. So kind of a common trick is, if we want to show that the absolute value of x sub n minus x is less than epsilon, we need to show that this whole thing is less than epsilon if we can. And if we can, one way to do that, if we can, is to show this part is less than epsilon over 2, and this part is less than epsilon over 2. Now wait just a second. This part right here is easy to control, because x sub n sub k is a term from the subsequence. And I know that the subsequence converges to x. So I push far enough along with the k's such that this thing is small. Is that okay? I can do that. That's easy. How am I going to control this guy? Well, the way that I'm going to control this guy is x sub n sub k is a subsequence, or a term from the subsequence. That means it's a term in the sequence of x sub n's. But what do I know about the x sub n's? They are Cauchy. And so the terms between Cauchy sequence gets really, really small, gets close together if we push far enough along in the sequence. Is that okay? So I'm going to use both of those facts to make each one of these parts be small. Okay? So let me write those up. So since x sub n sub k is a term in x sub n and x sub n is Cauchy, there exists, I'm going to call it J sub 1, it's a known natural number, it's just a position in the sequence of x, such that for all, I'm going to say n and k greater than or equal to J sub 1, we have x sub n minus x sub k is less than epsilon over 2. Thus, for all n and k greater than, well, here's what I'll say. Thus, for all n greater than or equal to J sub 1, we have x sub n minus x sub n sub k is less than epsilon over 2 as n sub k is greater than or equal to k. That's something we proved. I'm going to stop, raise the board, give you a second to digest this and make a few comments. Okay. You know, I didn't write down what I wanted to. I'm going to make it x sub n sub j sub 1. That's what I wanted to write. So make that change. Give it back a second. Okay, what am I doing? Look, I'm just letting k be equal to j sub 1. Okay? And if k is equal to j sub 1, then k is bigger than or equal to j sub 1. And that means that x sub j sub 1, that being subtracted from x sub n, that's going to be less than epsilon over 2. So here, just imagine k being j sub 1. But that ain't what I wrote here. I wrote n sub j sub 1. So I guess I should write down n sub j sub 1 is bigger than j sub 1. Over here is the correction. So this right here says as long as the index is beyond j sub 1, the x sub that index, the difference between the two of them, those terms of that type, inside absolute values is less than epsilon over 2. Now, what I'm saying is that n sub j sub 1 is bigger than j sub 1. That's a fact we proved about a strictly increasing sequence of natural numbers. That was a fact that we proved by induction. So this term right here, this number right here, is a number that's bigger than j sub 1. So x with that index, it's a number bigger than j sub 1, bigger than or equal to j sub 1, minus x with an index that's bigger than j sub 1, it fits into this category. Both of the indices are bigger than j sub 1, so the terms in those positions, the distance from each other is less than epsilon over 2. Okay. Since remember what I just did is going to control the left-hand part of this two-term sum. Okay, it's going to control this guy. To control the right side, and since x sub n sub k converges to x, there exists a j sub 2 element of the natural numbers, such that for all n, or for all k, bigger than j sub 2, bigger than j sub 2, x sub n, or x sub n sub k minus x will be less than epsilon over 2. So we got these two spots running around.
I want to make sure that I have both of the occurrences happening. So I need to push to the what between J1 and J2?
The biggest.
That's right. So we let J equal to the max between J1 and J2. Then, here's what I look at. X sub n minus x. Remember, this is the guy that I want to show that's less than epsilon. Okay? I want to show you that this is less than epsilon. What I'm going to do is say, hey, that's the same thing as x sub n minus x sub n sub j plus x sub n sub j minus x, which is going to be less than or equal to, use the triangle inequality, x sub n minus x sub n sub j plus x sub n sub j minus x. Okay. So for all n bigger than or equal to j, I'm going to leave part of this on the board. So for all n bigger than or equal to j, we have absolute value of x sub n minus x, which is less than or equal to x sub n minus x sub n sub j, plus x sub n sub j minus x is less than this part right here. Due to the cosinus, we're taking two indices that are bigger than j. And if you're bigger than j, you're bigger than j sub 1. And if you're bigger than j sub 1, we have this property right here being less than epsilon over 2. So it's because of this property right here, and that's why I'm leaving it on the board. I'm going to erase it now. Plus x sub n sub j minus x, that can be made, or that is very small, it's less than epsilon over 2, because the j here is bigger than or equal to j sub 2, okay? And the subsequence converges to x, forcing this to be as small as I want. I want it to be less than epsilon over 2. And that's equal to epsilon. So as two conclusionary statements to wrap it up. So for all n bigger than or equal to j, absolute value of x sub n minus x is less than epsilon. Thus, what do I know about x sub n? It converges. It converges to x, so x sub n converges. And that's what we were trying to show.
Question.
Yes, sir?
Does that x that we found that it converges to, does it have any relationship between what we started with and, like, I mean, do we still know what it converges to?
No.
Or not?
No.
So it's just.
It converges to something, and that x is what represents what it converges to.
Okay. Now, if we could find a subsequence that converges to something, then would we know?
Yes. So if you give me a Cauchy sequence and you see that a particular subsequence of it converges to something, what that particular subsequence converges to is what the whole sequence converges to.
Okay.
Yeah, that's what we were proving there. Is that okay with you? Well, ladies and gentlemen, that's about all I wanted to say, I think, having to do with Cauchy sequences. And let me make sure. Yeah, that's all I wanted to say. And the last part of sequences that we're going to study just in its own sake, just for its own sake, has to do with what's known as properly divergent sequences. So these are sequences that diverge, but they diverge in a special way. Okay, called properly divergent. So this is the last topic for sequence in and of themselves. As I erase the board to get some room to write up about properly divergent sequences, let me tell you two things.
One, I haven't got the next homework assignment ready, but it's close to time to get the next homework assignment. It'll cover what we've been covering about sequences, so it will include about monotone sequences.
That's okay, take your time.
It will include about Cauchy sequences, and it will include about these properly divergent sequences. Okay? So that's what we got coming up for us to look forward to. That's one comment. The other comment I wanted to make was that I said this is the last kind of topic about sequences that we're going to study directly. All right. So I'm going to make this comment. This is kind of an overview of a characteristic that I kind of associate to mathematics. And that is, in the branch of mathematics that I study, probability analysis, the way that I would describe things, the way things are set up, mathematicians set them up, is very nice in that we learn about something new by relating it to something we already know. Okay? So the last two topics that we're going to cover in this class has to do with functions, and the first of which are limits of functions. And we're going to relate limits of functions to limits of sequences. So the information we've been learning about sequences are going to help us be able to prove things about functions, limits of functions. And then the last topic is about continuity of functions, which are related to limits, in some sense, of functions and sequences. Okay? And so this material that we're learning about sequences is going to help us learn about other things. I really like that about math. One time someone asked me, how would you describe mathematics in general? I said, it's understanding the unknown from the known. That's what we do. We relate something that we don't know about to something we do. So well, it's got these same characteristics. Well, I think they do this. I'm going to shut up after this. I think they do this for like space exploration. You know, they send some rover to Mars. Well, how do they know what it's going to be like on Mars? Well, they don't exactly. But they say, we think the surface, the soil is going to be like, and they say, something like the desert. And so they go to build equipment that works on the desert so that they can have this rover maybe work on Mars. Does that make sense? And then they get samples from Mars and say, hey, it's kind of like the desert. Does that make sense? That's what they do. So math has that too. I like that a lot. Okay. Well, that doesn't have anything to do with the properly divergent. That was a little bit too abstract, maybe. That was opinion. But what is a properly divergent? Well, the first thing is properly divergent. It's a catch-all phrase. It's like saying monotonic. But really, when we said monotonic, we broke that down into two categories. You were either increasing or decreasing. Well, we're going to have two types of properly divergent. So here's the definition. A sequence. Oh, let me write this down first. As a definition. So, definition. I'm going to write down notations. Okay, I'm going to get down. Notation. It's simple. Right there. Do we know what that's called? Yes. Means going on forever in the positive direction without bound. And that's what it means. And we've had, as n goes to infinity, but I don't think I've ever said, what do we mean by infinity? Well, that's what we mean. We mean getting bigger and bigger and bigger without bound. That's the first thing. And then we got this other symbol, it's kind of similar to that. Minus infinity. And that means going on forever in the negative direction. Without bound. So I don't think I've ever given an idea of these
two symbols, but I should have, and there it is now. Well, Chuck, from that, we want to talk about a sequence going to infinity or minus infinity. So let me write it down in terms of notation. Yes. So, as a definition, a sequence x of n tends to infinity. If for each, I'll say alpha element of R, so for each real number, wait a minute, what does it mean to go to infinity? It means you get bigger than any, not maybe it doesn't do that, maybe it could bounce around a little bit, but that it gets bigger than any number. Is that okay to go to? And we're going to kind of get that involved, but we're going to get more than that involved in this definition. So, if for each number you give me, alpha, there exists a k element of R such that for all n bigger than or equal to k, x of n is bigger than alpha. So I said we're going to get more than just get bigger than any number you give me. So here's what this is saying. It says no matter what number, if you're going towards infinity, if you tend towards infinity, that means that no matter what number you give me, that's called alpha, there's a spot in the sequence such that every term from that spot and beyond is bigger than alpha. So not only do you get bigger than alpha, you stay bigger than alpha from then on. John.
Why don't we want k to be a natural number?
Oh, we do. Yes, it's a spot. I made a mistake. Thank you very much, John. This is denoted by the limit as n goes to infinity of x of n equals to infinity.
And same thing you said about going to minus infinity.
And we will. Yes, sir. So definition. If we talk about going to infinity, we ought to be able to talk about going to minus infinity. A sequence. X of n tends to minus infinity. Go ahead. If for each alpha element of R, there exists a k element of n such that for all n bigger than or equal to k, we have that x of n is less than alpha. Okay, that's the same idea. To go towards minus infinity means the following. No matter what number you give me, there's a spot in the sequence such that from that spot on, all the terms of the sequence are less than the number you gave. So to go to minus infinity, got to get smaller than every number, but not only do you have to get smaller than any number you give me, we get smaller and stay smaller. This is denoted by it's the limit as n goes to infinity of x of n equals to minus infinity. That's what we do know. For those of you who don't know, Alabama lost their last basketball game of the season on Saturday. They played a good first half, but weren't scoring enough points for the second half. I know you're all interested. I think Alabama's basketball fortunes are about to turn around. Alabama's willing to pay lots and lots of money right now to get good basketball. Lots. And so the athletic department making lots of money. And that's what we're going to spend.
I wish I coached basketball.
They're going back to lay out $4.5 million for somebody.
$4.5 million.
That's not what I'm making. Okay. All right, so we have another catch-all definition. A sequence X of n is said to be properly divergent if either x of n tends to infinity or minus infinity. So properly divergent is this catch-all phrase. If you tend to infinity or minus infinity, we say that you're properly divergent. You're divergent. You didn't converge to a number, but you diverged in this special way. Okay? Corey?
So would that mean that we wouldn't be able to find a subsequence that converges?
That's correct. That for some of these examples, you can't find the subsequence that converges because it's not bound. That's correct. Well, let's look at some examples to get maybe a better feeling. So what if I looked at the example, let's say minus 2 to the n. Then the limit as n goes to infinity of minus 2 to the n equals to minus infinity. I'm writing it down. I'm saying it's properly divergent. How come? Well, I'd say it's going to minus infinity. How would we prove that? Well, I'm erasing how we would prove it, but the way we prove it is using the definition. You know, it's really easy to say, well, look, I mean, n's getting really huge. It's a positive number. You multiply by negative, it gets to really big, huge, in magnitude, negative number. So it's getting smaller than anything you want. That's the idea. But in my opinion, the beautiful thing about mathematics is we don't only capture ideas. We give verifiable means by which to justify a statement. So I'm thinking it goes to minus infinity. How would I show that? I've erased the definition. But here's the way I would show it. So here's my proof. We would let alpha be an element of R. Remember the definition said, hey, no matter what real number you gave me, we could find a spot such that from that spot on in the sequence, all the terms would be less than alpha. So I said, no matter what alpha you gave me, well, all right, here's an alpha. I don't know what it is. Somebody gave me an alpha. I don't even know what it is. Doesn't matter. No matter what it is. We need a k element of natural numbers such that for all n bigger than or equal to k, x of n will be less than alpha. So we want, well, what is it that x of n is? What's its expression?
Minus 2n.
We want minus 2n, that's right, Alpha. That's right, John. To be greater than, to be less than alpha. The goal here is to solve for n. So how would I solve for n?
So 9 minus 2 on both sides.
Alright, so we want, that would say n to be greater than alpha over minus 2. And switch the sign because of the inequality, because I divided by a negative. Okay.
Archimedean property.
By the Archimedean property. That's right, John. Excellent. There exists a k element of natural numbers such that k is bigger than alpha over minus 2. So, for all n bigger than or equal to k, n will be greater than alpha over minus 2, which is what we wanted. I'll write it down, so for all n bigger than or equal to k, minus 2n. I multiply both sides by minus 2, so I have to switch the side of the, switch the direction of the inequality, is less than out. That's what I need. I'll write it. Thus, limit as n goes to infinity of x of n equals to minus infinity. For me, Melissa, man, right here is good enough to call it quits. You don't have to do the going forward direction. Okay, Chuck, I would quit there. I found the K I was looking for. I'm good. But I just wanted Corey to finish it up that way to show that you can list the forward direction. You remember when I was doing proofs involving convergence, I said once we find the K, we're good. We don't have to do it backwards. Okay, so that's what I feel here too. Anyway, next time we'll do another example of a sequence that properly diverges to infinity, and then I'll look at an example that doesn't converge, but doesn't properly diverge, but yet is unbounded. All right, that's good enough for this time.